name is Kelly Barraza. I'm the managing editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information to ASHRAE Journal readers and others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by Condair. The subject is Adiabatic Solutions for Data Centers. Today's speakers are William Trong and Sean Bartlett. William Trong serves as the North American Business Development Manager for data centers at Condair. He specializes in integrating adiabatic technologies, including evaporative media and atomizing nozzle systems into both new and retrofit data centers and products. William holds a bachelor's degree in mechanical engineering from the University of Ottawa and currently chairs ASHRAE TC 5.7, evaporative cooling. Sean Bartlett has had various engineering, project management, and leadership roles in the water treatment industry, supporting customers in the power, semiconductor, and oil and gas markets. His knowledge includes water chemistry, the system design, and operations optimization. Before Sean joined Condair, he worked as a facilities chemical engineer with Meta Platforms, supporting critical cooling systems at multiple data center campuses. Sean earned his bachelor's degree in chemical engineering from Northeastern University and a master's in environmental engineering from Johns Hopkins University, and is currently the workstream lead for Open Compute's Direct Evaporative Cooling Best Practices workstream. Will, the mic is yours.
Perfect. Thanks, Kelly. So again, thank you everyone for taking your time to join us for today's webinar. Bit of housekeeping to start. We do have a bit of an hour time slot for the presentation. So we'll take about 40 to 45 minutes for the actual presentation itself. And then we've got about 15 to 20 minutes reserved for questions at the end. So you'll notice that there is a Q&A box where you can type in your questions at any point during the presentation. And then we'll do our best to answer as many as we can at the end. Any questions that we don't get to answer today, we'll be sure to follow up with you all individually after the webinar as well, addressing your questions. So with that, let's take a quick look at today's agenda. So the topic is adiabatic solutions for data centers. So we'll cover both adiabatic cooling and humidification solutions. And at a high level, we'll cover the difference between isothermal and adiabatic humidification or cooling systems. Then we'll move on to the types of data centers where these are commonly used. And then we'll look at economization and why it makes sense to combine that with direct evaporative cooling or some sort of adiabatic cooling system. Then we'll move into the main adiabatic technologies that are available today, and we'll end with a case study that actually illustrates the potential energy savings moving from a more traditional compressor-driven cooling system to an adiabatic type system. So we'll start with methods of humidification and evaporative cooling. So there's a couple ways that we can humidify or cool the air, and the processes that we're going to look at here are what we refer to as the adiabatic process or an isothermal process. Now, thing to keep in mind here is in both processes, we're evaporating water into the air to increase that moisture content. Now, the amount of energy needed is the same regardless whether it's an adiabatic or an isothermal process. So it's about 1,000 BTUs per pound of water evaporated. So that is really the energy needed to drive the phase change between liquid water and vapor. So if we look at an adiabatic process, we are actually relying on the energy from the air to drive that phase change. So this can be done a couple different ways. The first is by atomizing the water or spraying the water into an airstream where those droplets are then evaporated. The other way that this can be done adiabatically is by passing that warm, dry air through an evaporative media where that water is evaporated off of it, and we get cool humidified air on the discharge side. Now, in comparison, an isothermal process is where we're actually putting energy into the system to drive that phase change. So essentially boiling the water and creating steam, which is absorbed into the air, increasing that humidity or moisture content. So if we look at the adiabatic process to start on a cycle chart, it's essentially a constant wet bulb process. So because we're pulling energy from the air, in addition to an increase in humidity, we do also have a cooling effect with it as well. So it ends up being about 0.3 kilowatts of cooling per pound of water that we're evaporating. So this is one of the main reasons why this is such a great technology and such an efficient way to cool and potentially humidify a data center, or really any application that requires year-round cooling as well as potentially some level of humidification. Now, the caveat here is really in order to maximize that cooling effect, we want to evaporate as much water as possible. So in reality, what that means is if we're trying to maximize cooling, we could potentially be looking at humidity levels in the range of 80+%. Now, there are ways to take advantage of that adiabatic cooling effect without adding moisture directly to the supply airstream, and we'll touch on that later on. Now, if we look at, in comparison, the isothermal process, as I mentioned, in this case, we're simply adding energy to the system to drive that phase change from liquid water to vapor. So that energy source is typically electricity or gas, either natural gas or propane, and we're effectively boiling that water to generate steam, which is then absorbed into the air, thus increasing that humidity. So we consider this effectively a constant temperature process. In reality, depending on the method of steam distribution, which is typically a steam grid in the airstream, distributing steam into that air supply, there may be in reality a 1 to 2 degree temperature increase, but for any of the calculations that we're doing, any of the processes that we're looking at, we're effectively assuming this is a constant temperature process. So again, if we just compare those two processes, an adiabatic process is an increase in humidity with a temperature decrease. An isothermal process is an increase in humidity at constant temperature. Now, if we compare the energy requirements between those two processes, depending on the type of system, for example, here, if we're evaporating 200 pounds or 24 gallons of water, a typical electrode steam humidifier would consume about 75 kilowatts of electricity. Now, if we compare that to an evaporative media system, where the only energy really needed here is to pump the water to the top of the pads, a system like that could consume less than about 0.3 kilowatts. Now, the other thing to consider here is with adiabatic or cold water systems is that the potential capacity or the evaporation rate really depends on the entering air conditions and the air volume. So if we were to look at one of our evaporative systems, for example, you could potentially output 2,200 pounds an hour while still consuming less than 0.3 kilowatts of electricity, since we're still using the same number of pumps and we're still pumping water to the top of the media. Now, as a comparison, if we were able to evaporate 2,200 pounds an hour and the air was able to absorb that, we could potentially cool that air or provide about 700 kilowatts of cooling capacity in addition to that moisture content increase. So you can see that for large evaporation rates for either humidity or cooling, adiabatic systems do make a lot of sense efficiency-wise. And our general recommendation here is to look at or even consider adiabatic type systems for humidification loads or cooling loads over about 200 to 250 pounds an hour, which is really the point where they start to make sense economically, both from a CapEx and OpEx point of view. But again, here, the main consideration is if you're looking at this strictly for humidification and you don't necessarily need that cooling effect from an adiabatic system, you would need to consider either preheat or reheat requirements that may offset some of those potential energy savings moving to a cold water or adiabatic system.
Thanks, Will.
So yeah, with that, I'll pass it over to Sean here.
Sure. So when we look at data centers, there's really a wide variety of data center sizes, configurations, and cooling requirements. And for each of these situations, we see really different types of cooling systems. So we're just going to spend a couple minutes and go through some of the major ones. So the first type of data center that we're going to look at is a hyperscale data center. Well, there's really no official definition of what a hyperscale data center is. For the purpose of this discussion, we're really talking about large, purpose-built facilities specifically designed to house a very large number of servers. The number of servers at this point can be easily in many thousands. In this type of facility, it's more and more common to see the owner and the operator design really every aspect of this facility. So the building layout, cooling systems, the electrical systems, and really increasingly more, even the IT equipment operating inside. So having this really full holistic design can help streamline the operation and allow for a far more aggressive set of operating conditions and lower resource consumption. Just given public announcements, many of the large data center hyperscale operators at this point are operating their IT inlet temperatures close to or above 90 degrees Fahrenheit. Well, these facilities can definitely use all different types of cooling. In the past 10 to 15 years, many of these facilities have been created to leverage economization as much as possible, with one popular option being direct evaporative cooling. Direct evaporative cooling systems allow for a very low power consumption and very moderate water consumption when used with low to medium density IT equipment. And given the really large size of these facilities, even small efficiency gains can lead to large absolute savings. Next, we have co-location data centers. The co-location data center market really has an incredibly wide range of facility sizes. There can be some as small as a couple of megawatts, though recently there's been a lot of news of incredibly large campuses in the hundreds of megawatts. So these facilities are really starting to rival hyperscale facilities in their size. So the co-location market tends to be a little bit different as the operators are renting space. So the space can be as small as a single rack, it could be a data hall, or even entire buildings can be rented to customers. In this type of facility, it's common for the co-location operator to manage the facility side of the building and maintain critical parameters such as temperature and humidity through service level agreements, while the individual or organization renting space manages the IT equipment. So in this type of situation, given the potentially wide variety of IT equipment in the facility, temperature and humidity levels are typically operated at a much more conservative range compared to hyperscale facilities. Due to these requirements, use of direct evaporative cooling is definitely less common. While we've seen it in some of these facilities, it tends to be more common to see chilled water systems and crawl units or crack units. Though when we do see facilities with crawl and crack units, it's still common to see the use of either standalone humidifiers or humidifiers built into the cooling units to provide some control over that parameter. So the next thing we want to talk about is pre-cooling. Well, pre-cooling is definitely not a type of data center. It's an application for adiabatic systems. Pre-cooling of equipment such as chillers and fluid coolers is not new. It's been around for many years. So we're definitely seeing an increased interest in this application due to rising power constraints in the data center industry and the shift to liquid cooling, requiring the use of chilled water systems and mechanical cooling. So in these types of systems, the air is used to cool equipment, and it can be lowered to a value close to the wet bulb temperature of air. Lowering the temperature of cooling air can allow for the mechanical equipment to either be sized smaller or operate at lower levels, decreasing power consumption. So if we look at this diagram that we have on this page, it's representative of something like an air-cooled chiller, with the blue being the condenser coils and brown being the adiabatic cooling media. For example, if this application had air with a dry bulb of 104 degrees and a wet bulb around 70 degrees Fahrenheit, the adiabatic media could cool the air to around 78 degrees. So this would allow the system to be cooled with air that's about 26 degrees colder. The use of pre-cooling can also be set to only turn on when certain conditions allowing for an optimized use of both power and water at the facility. There's definitely other types of data centers worth mentioning, things like enterprise data centers, edge, and containerized. These facilities definitely tend to be smaller compared to the two other types of facilities we discussed. While as a company, we've seen evaporative cooling used in these applications, it's definitely not common, as there's a higher level of investment required to have the facility connected to both water feed and sewer connections. Also, the maintenance tends to be higher compared to other cooling technologies such as direct expansion. So the next thing that we want to discuss is economization and how this can be used with adiabatic systems. So before we get into how economization is accomplished, it's good to do a quick review of thermal guidelines for IT equipment. Arguably the most important document for the design and operation of IT equipment in data centers is ASHRAE's Technical Committee 9.9's Thermal Guidelines for Data Processing Environments. The document has been around for over 20 years and has gone through several revisions since the original release. The original release had a pretty limited recommended range, about 68 to 77 degrees Fahrenheit, dry bulb, and 40 to 55% relative humidity. Though, as you can see from the chart to the right, it's really greatly expanded in the last 2 decades. The recommended temperature and humidity ranges are ideally where IT equipment operates the majority of the time, though there have been a number of allowable ranges added that allow the envelopes to expand beyond the recommended range. It's generally acceptable for IT equipment to operate in these allowable ranges for limited amounts of time with negligible effects to reliability. As the temperature and humidity ranges have grown, it's really presented an opportunity to greatly reduce requirements for mechanical cooling. In the last decade or two, many facilities have been designed to leverage economization even 100% of the time and completely eliminate the need for mechanical cooling and air humidification. Now we can look at a little bit more into how economization is accomplished. So to be clear, economization is not a piece of equipment per se. It's a mode of operation that allows part of your cooling system, say such as a chiller, to shut down or reduce load, saving resources. So there's a number of different ways that economization can be accomplished. The 3 main ones that we'll go over are air side, water side, and refrigerant-based. In air side economization, outdoor air is brought directly into the data hall when temperature and humidities are within an acceptable range. With this type of system, the outside air can also be cooled and humidified with equipment such as an evaporative cooler to increase the potential hours for economization. In water side economization, chilled water from a cooling system is either fully or partially bypassed around the mechanical cooling equipment and allowed to reject heat directly to equipment such as a fluid cooler or a cooling tower when those pieces of equipment are able to provide sufficient cooling. The last one is refrigerant-based economization. In these types of systems, refrigerant in a system such as a direct expansion system is used to complete the refrigeration cycle without the use of mechanical compression. Though it is important to note that refrigerant-based systems tend to be more proprietary and can be unique to the specific supplier. And both the water side and refrigerant-based systems can still definitely benefit from the use of pre-cooling to increase the potential hours of economization by improving outside air conditions. So to further examine air side economization some more, we can look at the number of hours per year an evaporative cooling system would have to operate to maintain different operating envelopes. What we're looking at here is what we kind of call a legacy, definitely that colder temperatures and the recommended envelope, and then also 2 of the allowables. So outside of the hottest regions in the United States, so places like Texas and Phoenix, a direct evaporative cooling system would only have to run about 1,500 hours or less when cooling to the recommended temperature envelope. Though if that same facility was allowed to utilize the allowable envelopes, these hours drop pretty substantially. So as Will mentioned, since evaporative cooling technologies use very little power to operate, the primary resource being consumed is water. Therefore, reducing the hours of wetted operation is a great way to reduce water consumption and improve sustainability. But one way to think about this is almost economizing your economizer. So with that, I'm going to hand back off to Will, and he's going to go over different types of adiabatic systems.
Perfect. Thanks, Sean. So yeah, let's jump right into the technologies that we see available in the market today. So the 3 technologies that we'll be covering today are wetted media systems, atomizing nozzle systems, and what we call ultrasonic or nebulizer type systems. So the first type of system that we'll look at here is what we call a wetted media system. If you guys have heard the term swamp cooler before, it's effectively the same thing. What we have here in this system is a wetted media placed directly in the airstream. That wetted media is typically a glass fiber based media. Depending on the application and where this is being installed, we do sometimes see a cellulose or paper based media used as well. But effectively, we are placing that media directly in the airstream. As warm, dry air passes through that media, water is evaporated off, and it cools and humidifies through that adiabatic process that we talked about earlier. Now, the thing to keep in mind here is that all of the evaporation takes place within the depth of that media itself. So if the system is designed and operated correctly, there really shouldn't be any water carrying past that evaporative section. So that makes this type of system really great for retrofit applications as well, because you can typically fit these into a tighter space compared to some of the other adiabatic technologies that we'll talk about that do require a bit more unobstructed airway length. Now, in order to reduce the overall water usage with this type of system, any water that is not evaporated typically falls into a sump. In that sump, we typically have a recirculation pump that is used to recirculate and pump water to the top of the media. Now, in terms of where the system is typically installed, we would typically see this between a heating coil and a cooling coil, which allows for any potential preheat that's needed, as well as additional cooling that is potentially needed, or control of the leaving air conditions using that cooling coil that is downstream. Now, one of the main benefits to using an evaporative media system over some of the other technologies that we'll talk about is that a media system can operate on most water qualities. So unlike atomizing systems or ultrasonic units, systems that we'll talk about, those systems do require treated water, so either reverse osmosis or deionized. But with wetted media systems, we are a bit more flexible in terms of the type of water that we can put over the media. Now, if we're using, mains water, potable water, or well water, or any water that has minerals in it, as that water is evaporated off of the media, those minerals, whatever is in there, will start to concentrate up, and over time, we will potentially start to see a scale form on the surface of the media. So with most systems, as a means to control or help reduce that mineral buildup, the systems will typically perform a blowdown cycle, drain some water out, bring in some fresh makeup water in order to maintain media life, as well as kind of optimize the water usage as well. And there's a few different ways that water quality can be controlled. So we cover this type of system along with water quality considerations, cycles of concentration in one of our previous ASHRAE webinars, which we'll link at the end of the presentation as well. So if you are interested in learning a bit more about this technology in particular, we will link that webinar at the end of this presentation. So with this type of system, as I mentioned, very little energy is really required to operate it. Really, it's just the power needed to pump water over the top of the media. There will be some additional fan power required to overcome the pressure drop across that media, but really in comparison to a traditional isothermal humidification system or even a DX cooling system, the amount of energy that we're using here is significantly less. Now, a consideration that you should keep in mind here if you're looking at or considering a wetted media system is on the controllability side of things. So because we're pumping water to the top of the media, we're relying on gravity to pull that water through the pad itself or through the media itself. That media is going to take time to fully saturate and hit maximum kind of performance, as well as once we hit that point, it's going to take some time for that media to dry out as well. So typically with a wetted media system, it is going to be a bit slower to respond to changes in demand. So if you do have requirements for tighter control, tighter temperature or humidity, leaving air conditions after this section, you may want to look at implementing different control strategies, so bypass control or even phase and bypass control if you do need those kind of tighter conditions. So the next technology that we'll talk about here is what we call high pressure atomizing systems. So in this case, the system works by spraying high pressure water, typically at about 1,000 PSI, directly into the airstream where it's evaporated. So because we're spraying at fairly high pressure, droplet sizes here range in kind of the 10 to 40 micron range. So we do still get very, very good evaporation because of the size of those droplets. Now, if we compare that to an evaporative media system, these will typically consume a bit more energy. Again, because we do need treated water, so that's either reverse osmosis or deionized water, so there's going to be energy associated with the water treatment side. And then we do also have a high pressure pump motor in there as well, but still significantly less than a traditional humidification or DX cooling system. So to give you an idea here, a system capable of outputting about 1,700 pounds an hour will consume about 3 kilowatts of electricity. Now, because this system is actively atomizing the water, the evaporation efficiency here will depend on the contact time between the air and the water. So we typically see a minimum of about 3 to 5 feet of unobstructed airway length, really in order to achieve a decent evaporation efficiency. So with this system, again, any unevaporated water, primarily for hygiene reasons, is not recirculated within the system. Any water that's not evaporated will typically get caught by what we would have downstream as a mist eliminator or potentially the cooling coil to prevent any water droplets from carrying past that section, potentially wetting components downstream. Now, the efficiency will also depend on the entering air conditions, so the temperature and the relative humidity, the air velocity, as well as that available absorption distance. So with higher velocities or even shorter absorption distances, that contact time is going to be shorter. So we would typically expect a lower evaporation efficiency in those types of conditions. For both systems, evaporative media and high pressure atomizing systems, we do generally try and design around a 400 to 500 feet per minute air velocity or duct velocity. So as I mentioned, with this system, we do need treated water. So that's either reverse osmosis or deionized. Really, the main requirement there is to ensure that any minerals that are in that water that we're spraying do not precipitate out as a dust as those droplets are being evaporated. Those can potentially clog the mist eliminators. They can potentially make their way downstream into the space. And then it's also important to have the treated water to ensure that we're not clogging those nozzles. So because we're, spraying that water through a very, very fine orifice, any type of clogging can cause issues with dripping or clog the nozzles themselves. Now, the big difference here between evaporative media systems and a high pressure atomizing system is on that control side. So as soon as we have a demand for humidification or cooling, the pump will turn on and we will start spraying water. As soon as we hit that point, we'll turn the pump off and we'll stop spraying water. These systems are also capable of staged control or modulating control. So with this type of system, we're able to achieve accuracies in the range of plus or minus 2% on the discharge side, in comparison to, say, an evaporative media system without any other kind of control schemes there. We're looking at probably plus or minus 5 to 10% control. So the other nice thing about the high pressure systems compared to the evaporative media systems is we can a lot of the time build these for full redundancy, so N+1 redundancy, and also have the ability to control multiple zones, each with their own set point from a single pump station. So for example, if you had 3 or 4 air handlers, each feeding different zones, each with different humidity or cooling set points, you could potentially combine those and feed them from a single high pressure pump station, but still be able to maintain individual control at each of those zones. Compared to a direct evaporative media system where we would need an evaporative system in each of those zones. So both of those technologies that we just looked at are commonly applied in what we call a direct evaporative system. So in this case, the adiabatic system is placed directly in the supply air stream, and we are cooling and humidifying that air that is supplied directly to the space. So this type of configuration is really ideal for hot, dry climates where the air can hold more moisture and allows for the highest amounts of cooling. With this system, however, it does typically require higher ventilation rates in order to maintain that cooling capacity. So it's not really suitable for humid climates where evaporation is limited as well. Now, the other consideration here with this type of system is on the filtration side. Because we're bringing in a lot of fresh air, it's important to make sure that we do have proper filtration here to keep out any kind of outside particulates or contaminants from entering that supply air stream. Now, the other way that we can apply these is through what we would call an indirect cooling system. So in this case, the airstream is cooled adiabatically. So with one of the systems that we've talked about, passed through a heat recovery system, then exhausted out. The supply airstream to the space, which can be recirculated from the space, is indirectly cooled from the other side of that heat recovery unit. So this allows for the supply airstream to be cooled adiabatically without adding moisture and eliminates the risk of any outside particulates or contaminants from coming into the space. Now, the amount of cooling that we can achieve here can be increased by circulating more air, and we're not really limited here to the extraction or the fresh air rates like we would be with a direct cooling system. The thing to keep in mind here is that the efficiency of this type of system can also be increased if we were to put a direct evaporative cooling on the cool air supply as well. So effectively a indirect direct type system. So generally this type of system will also have a higher cost compared to a direct evaporative application. And the efficiencies here will depend on the efficiency of that heat recovery system as well. So the last technology that we will look at here is what we call ultrasonic or nebulizer type systems. So the way that these systems work is we have a series of piezoelectric transducers submerged inside of a sump. Those transducers oscillate at an ultrasonic frequency, which causes cavitation in the water, and that releases an ultrafine mist into the airstream. So very similar to high pressure atomizing systems, with ultrasonic systems, we do need treated water as well. So either reverse osmosis or deionized. And again, main reason here is to prevent any of those minerals from precipitating out as a dust as that mist evaporates. And then also to prevent clogging of or scaling of the transducers. Now, in terms of design considerations or use of these types of systems, thing to keep in mind here is these are typically smaller capacity systems and outputs ranging in the 5 to 40 pound an hour range. So for that reason, we typically see ultrasonic systems as a more cost-effective way to humidify data centers, small data centers or small computer rooms. So just to give you an idea here, a typical 40 pound an hour ultrasonic unit would consume just under a kilowatt of electricity. And that would be a system with an integrated kind of fan blower like you see in the picture here. Now, these systems are typically installed directly into the space with the blower pack. Like you see here, some units can be installed inside of a duct or an AHU as well. Now, the thing to keep in mind if you're doing that is, of course, on the absorption distances. So because it is a cold mist, we're going to have a plume or visible absorption distance, just like we would with a high pressure atomizing system. Now, with these, we see typical absorption distances in the range of 10 to 15 feet. But again, that really is going to depend on the conditions and where this unit is installed. So of course, warmer, drier conditions where we absorb that water a bit quicker will have much shorter absorption distances. The other nice thing about these type of systems is this would meet California's Title 24 energy requirement for humidifiers in computer rooms, which specifically restricts the use of isothermal humidification rooms in data centers or computer rooms over a certain size. So this could potentially be a good fit for some of those smaller data centers that do need some level of humidification in California. So those are the kind of three main technologies that we see in the market today. What I want to end here with is just a case study. And this is a case study for a UK-based AHU manufacturer called Weatherite. The objective here was to replace existing 30 kilowatt compressor-driven cooling systems with a refrigerant-free, energy-efficient solution for low to medium-sized telecoms rooms for one of the leading telecoms providers throughout the UK. Now, one of the design requirements for this system was that it did need to match the footprint of the existing system, so they could be retrofitted or swapped one for one. And they did also want to look at direct evaporative cooling as well. So this is a really great example because it shows that evaporative cooling can still be an energy efficient and economical solution on smaller scales as well. So you don't have to be deploying this at the hyperscale level to really take advantage of this type of technology. So as Sean had talked about with the economizer operation, in this case, evaporative cooling isn't always required, and actually for several hours out of the year, the design set points could be met using fresh air only. So this system actually has two operating modes. So mode 1 is what we would call free cooling mode with the bypass damper open. So how this works is at the top of the unit, we have the recirculating air damper. So if that is open, we can actually recirculate air, mix that with fresh air from the outside and supply that to the space. If that circulating air damper is closed, we can exhaust air as well. On the right side, we have the fresh air supply coming in. And then, as I mentioned, because this is a direct evaporative type system, there are filters installed on here as well. So when the cooling demand can be satisfied with circulating air, fresh air, or a combination of the two, where they can mix in the supply air section and be supplied to the space, the system would be operating in mode 1. Now, if you look at the unit itself, so inside the cabinet here, you can see kind of a brown material. That is our glass fiber media that is installed in a full recirculating evaporative module and would come into play when we look at mode 2. So mode 2 would activate when the demand cannot be satisfied using outside air only. So in this case, we would turn on the evaporative cooler and pass air through that system. So in this mode, the bypass damper is closed. We force all of the fresh air through the evaporative module. We cool and humidify on the discharge side. And then we do have the option here to mix that with recirculating air as well. And then that is supplied to the space. So as I mentioned, this is a fully recirculating unit on the evaporative module as well. So in order to increase water efficiency and optimize the media life, we do have periodic drains on this system, and then we are recirculating that water that is not evaporated through that initial pass. So overall, you can see a very simple system, but can yield some significant savings that we'll look at here on the next slide. So what does that actually show or mean for the overall efficiency compared to the previous DX cooling system that they were using? So on the slide, we're comparing the annual energy consumption for both the legacy 30 kilowatt fresh air unit with DX cooling and the new 30 kilowatt adiabatic unit. So the top two rows of the table here show the ambient air temperatures from -5 to 35, and then the associated mode that we would be operating in based on those ambient conditions. So you can see here anything less than about 20 degrees C, both systems, the legacy DX cooling mode and unit and the 30 kilowatt adiabatic unit, would be operating in free cooling mode only. Above 20 degrees C, depending on the system, we would either be operating in adiabatic cooling mode or we would be operating in DX cooling mode. The next two rows show the cumulative energy consumption, which is calculated based on the number of hours out of the year at that ambient condition and the operating mode. So we're effectively comparing both of these throughout the year, looking at those specific operating modes and the hours that they are operating within those modes. So you can see that for the free cooling mode only, there is a slight energy reduction on the adiabatic side or adiabatic unit, and that's really primarily because of a more efficient fan motor and fan blades, but for all intents and purposes, relatively close because they're both running in free cooling mode. Where we see the significant energy reduction is when we start reaching that 20-degree ambient air temperature and we have to turn on the adiabatic cooler or operate in DX cooling mode. So the majority of those savings is actually between 20 and 30 degrees, and you can see a significant decrease in the total amount of energy needed to operate these two systems. So if we look at that totaled throughout the year, going from a 30 kilowatt DX cooling system to a 30 kilowatt direct evaporative system results in about 80% less energy consumption for the same type unit. So you can see that, you know, with this type of system, it really does make sense if you're in an area where you can take advantage of that, that free cooling. Now, if you are interested in learning more about this case study, we do have more information, more details available, along with some additional kind of figures and numbers available on our website as well. So we'll link that on the next slide. So we've got a few slides here, or a few links here. So that concludes the presentation portion of our webinar, but on this slide, we've got QR codes that will link the full case study that we just talked about. We've got the previous webinar link there as well, which is titled Efficiency Gains Achieved by Moving to ASHRAE Allowable Temperature Ranges at Data Centers with Direct Evaporative Cooling. So if you're interested in learning a bit more about the direct evaporative media systems, water quality, COCs, be sure to check that out. And then we do also have our website linked here if you are interested in learning about any more of the technologies that we spoke about. And then, of course, we've got our LinkedIn page here if you'd like to connect. So that wraps up the presentation portion of the webinar. So I think we've got about 15 to 20 minutes here open for questions. So I see we've got a few that have come through.
Well, I can start.
Sure.
So there was a question: is the media replaceable because of hard water / contamination? So it's in general, yes. It's a little bit specific to the air handler OEM who is making it. Though generally the media lasts about 5 years, so there is an expectation, typically almost always, to replace the media multiple times throughout the life cycle of the air handling unit. So if we look at the Weatherite unit, you can see the media in here. This is cassetted media. Media can come in either cassettes or just freestanding. The cassettes tend to make installation and removal a little bit easier, though there is some cost associated with that. So in this unit, you would disconnect the recirculation hose, you would undo some bolts, you pull the cassettes out, and you put new ones in. It's pretty straightforward.
Perfect. Thanks, John. There's another question here. I think this one came in right as you were bringing up that slide on the TC99 recommended windows, but it is, what is the recommended relative humidity level for data centers today? I've seen, or I've understood the RH levels is less than before, closer to 25 to 30%.
Sure. So let me see. So I would recommend that anyone that does work in this field does get themselves a copy of Thermal Guidelines for Data Processing Environments. It's a very, very good document. There's also some free handouts. So the recommended range right now, what's in green, dry bulb is 64.4 to 80.6 degrees Fahrenheit. The upper range is either 70 or 50% relative humidity. In the most recent release, there have been some stipulations of upper relative humidity based on corrosion potential in the air. So if your air is a little bit more corrosive, then it's a slightly lower recommended relative humidity. In the recommended envelope, it's actually not a relative humidity at the bottom. It's a dry bulb. So it's 15.8 degree Fahrenheit dry bulb on the lower end. They'll go into the allowables. The lower relative humidity rate is 8% RH. That being said, this is guidelines. the specific recommendations for relative humidity and temperatures really have to be a coordinated effort between the IT equipment manufacturer and the facility operator. We did go into a lot more detail of this in the webinar that Will has mentioned previously.
Perfect. Thanks, Sean. There's another question here I can answer, asking about the velocity of air restrictions across the mediums. So, yeah, so as I mentioned, velocity, when we're talking direct evaporative systems or adiabatic systems in general, especially if we're going inside of a duct or an air handler or some sort of plenum, air velocity is going to play a big role in terms of efficiency and potential for carryover. So typically with an evaporative media system, we do try and design for around 400 to 500 feet per minute air velocity. Reason for that is once we put the evaporative module in, which typically consists of a sump, there's some distribution headers across the top. We've got some additional kind of metal and blank offs in there. We do typically see an increase in velocity or face velocity once we hit the media because we've lost some of that free area to the metalwork that we've got. In terms of restrictions or limitations, it's around 850 to 900 feet per minute face velocity onto the media for an evaporative media system, where we potentially start seeing issues or potential for carryover, which is water droplets coming down off of the media at those higher velocities. With a high pressure atomizing system, we do typically try and design for around 450 to 500 feet per minute because there's a lot less obstruction with that type of system inside of the plenum or the air handler. We don't typically see that large of an increase in velocity, but anything above around 750, 800 feet per minute, we would recommend an additional droplet separator as well. Now, in terms of efficiency at those higher velocities, both systems will have a decrease in efficiency. And really what that comes down to is a reduction in the contact time between the air and the water, whether that is off of the media or contact between the water droplets and the air.
Okay. Well, I see there's a question that I can take about can evaporative media be retrofitted to any air-cooled chiller? I would caution to speak in absolutes and say any chiller, because there are some considerations in terms of adding the increase in pressure drop and any potential physical limitations. But yes, generally it is possible to retrofit either a spray system or adiabatic cooling media to air-cooled chillers and fluid coolers.
Perfect. Got another question here I can answer. What are the typical sizes of these evaporative units? So the really great thing about the evaporative media systems and high pressure atomizing nozzle systems is they are very scalable and very modular. So at least with our systems, we do go as small as, I believe, 24 by 24, 24 by 36 inches. And then we do go full scale as well. We do custom units. The limitation on the direct evaporative media systems is about 4 meters in height. Above that, we would probably look at double stacking some of those units just to help with the water distribution. But these are very, very scalable units, and typically the way that they are designed, if they're going into a duct or an air handler or a plenum, is we would look at the available free area that we have or the available width and height that we have. And then we would size the unit really to maximize the evaporative section within there. To reduce the velocity through the media, which would help increase the evaporation efficiency, and then also help decrease the pressure drop across the systems as well.
So there was a question about what would the typical additional pressure drop be having an adiabatic system. Typical is a little bit hard. What I would recommend is that you go to a media manufacturer, such as ourselves, find the product data sheet for the specific media and look at it. There's a couple different considerations. Media comes in different flute heights, flute angles, and depths, and each of those factors will affect the pressure drop, and it's also dependent on the air velocity. Just as a quick kind of example, an 8-inch deep piece of FirePro in our typical configuration running at 500 feet per minute is less than 0.2 inches of water column. But it's going to be very dependent on the specific product you're looking at.
Perfect. Thanks, John. There's a question here. Can this be used in hospital HVAC systems for humidification with RO water per ASHRAE or CSA? So quick answer there is high pressure systems, yes. Evaporative systems, no. So ASHRAE 170 a few years ago did open up and allow the use of high pressure atomizing systems within healthcare facilities for humidification. So high pressure atomizing systems or atomizing systems are allowed. Evaporative media systems, as far as I'm aware, are still restricted. And then as for CSA approvals, we can look into that. I believe they were discussing opening that up to line up with ASHRAE 170 to allow high pressure atomizing systems, but I'm not sure if that has fully been vetted and passed through yet. So we'll make sure to follow up with you on that regarding CSA. But for ASHRAE, they do allow high pressure atomizing systems into healthcare facilities now.
Thanks, Will. So there's a question about for places where typical temperatures above 30 degrees Celsius, would DX cooling be the way to go? So I think the important thing to really consider with adiabatic cooling, it's more about the wet bulb depression and the humidity levels than temperature. We see a lot of these systems in either residential, commercial, and industrial in the American Southwest, which gets very, very hot. 120 degrees, would not be out of the question, but it tends to be very dry heat. So in those applications, these systems work very well. It's typically more of an issue when you have hot and humid, as there's a very limited wet bulb depression, and it prevents really effective cooling. So I'd say consider wet bulb depression and wet bulb more than the dry bulb when looking at adiabatic cooling.
Sean, there's a good one here for you. For evaporative cooling, can you analyze the water and give an idea of maintenance intervals and cycles of concentration?
Yeah, so there's definitely there's a number of ways that this can be done to calculate cycles of concentration. There's very simple ways. So again, if you go to a media manufacturer, they will typically have their specific parameter limit. So say 300 milligrams per liter of calcium. That's the simple way to do it. You divide that number by your input and you have a cycles of concentration. There are more sophisticated ways of doing that. Condor as a company can support that. So I'd say work with your engineer, your media manufacturer to analyze the water, because some of these are a little bit more advanced calculations to get the more accurate values.
Perfect. Thanks, Sean. There's a good one here I can answer. Do you have any issues with bacteria buildup over time? And if so, how do you address it? So that is a really great question. And, with any cold water or any adiabatic system, of course, hygiene and water quality and maintenance is critical, especially with some of the issues that we've seen with cooling towers and Legionella in the last few years. With a lot of these systems now, there are a lot of features built in, either on the water management side or as a mechanical means of controlling or managing hygiene. So, for example, with the evaporative media systems, you would typically see a UV lamp in the water treatment loop. The key with these systems as well is of course water movement. So we do try and avoid having any kind of standing water inside of the system. So depending on the application, we may see or recommend that the systems get drained every 24 hours without demand. On some of the larger data centers where they're more concerned about water, they may keep those for multiple days. But the key here is always going to be water management, and then any kind of any kind of mechanical means that we have. So we've got, like I said, UV lamps. We do dosing as well. So we can dose with the high pressure systems. We can dose peroxide and things like that to disinfect the water. So it is something that you do have to keep in mind when you are looking at applying any type of cold water systems here is on the hygiene side. Sean, question here maybe that you can answer. What about static electricity at higher humidity levels?
Sure. So typically, static electricity is not an issue at higher. It's an issue with lower. So once you're at kind of that 8%, that's more when you have issues. Definitely, this is something why any changes outside of the recommended envelope really need to be discussed holistically between any data center's facility side, the hardware engineers, site services, just to make sure that everything is being looked at as a whole. From my experience, I have seen the requirements for ESD mitigation when working on IT equipment, so things like heel grounders, discharge straps and such may have to be used, but that's really getting more into the IT equipment side, as that's pieces of equipment that are at most risk.
Perfect. Thanks, Sean. There's a question here I can answer. Can you elaborate on ways to achieve tighter control with the evaporative media humidifiers? Can it achieve plus or minus 2% at 70 degrees Fahrenheit? So, yeah, we had talked about that just very briefly, but in a few different ways that you can actually increase or improve the control accuracy with an evaporative media system is by using bypass control. So either having bypass dampers above or to the side of the unit or in the middle of the unit, or even face and bypass dampers. And really what that is allowing us to do is control to a mixed air condition downstream after the humidifier. So, once we hit set point, if we have face dampers, we can close off the airflow to the pads themselves, and then we can open up the bypass dampers and we can modulate or control to a mixed air condition from there. The other way that we've seen it done is a bit more inefficient, but is effectively dew point control. So you over humidify, overcool as much as you can, and then you use heating coils, cooling coils downstream to trim to your desired set point afterwards. So that's certainly going to be a lot less efficient way of doing it, but it is a way of achieving tighter control while still being able to use an evaporative media type system. So we've got probably time for one more quick question here. I see one. Can ultrasonic systems be used in a residential setting? They can. The only thing that you would want to keep in mind there is just that absorption distance. So generally with the smaller capacities, if you're just looking for humidification, the plume is going to be relatively small. But if you're on that higher end of the capacity outputs, in the 40 pound an hour range, you may have absorption distances, of 10 to 15 feet. So in a residential application, it's going to be a little bit trickier to do. There may be some systems out there, some smaller capacity systems that are designed for residential. From a Condair portfolio point of view, we don't have anything really smaller than kind of that 5 pound an hour range, but they certainly can be used. And there are other adiabatic or cold water technologies that are designed for residential applications. So I'll point you to our website. We've got a number of different technologies there that would be potentially better suited for the residential market if you're looking at an adiabatic type technology. So I think we're coming up on time here. There are a handful of questions here that we did not get to, but we will make sure to follow up with everyone here that didn't get their question answered separately via email. If you do have any other questions, feel free to reach out to us directly. And yeah, really appreciate everyone's time today. That concludes our webinar. So thanks again for taking the time to join us.